Okay. Let me start with a couple of announcements. There's homework due on Friday at the same time. There was some confusion as to whether 420 is as an assignment or not, and the answer is that it's not. So you don't have to hand that in. Any questions or comments? Yeah.
There's like a lab part, I guess, that you
Uh-huh.
never mentioned it in class the other on Friday.
Uh-huh.
Some of us just found out about it, so that's also due Friday.
There's a lab. Let me understand. The lab part is on the web page, but I didn't mention it in class. I wrote down a bunch of problems from the book.
Yeah,
There,
exactly,
it's
yeah.
not those problems that have labs. It's a separate
It's a
lab.
separate lab, yeah, with like a picture of a turtle and stuff.
I see. It's a picture of what?
I guess it's a turtle. I haven't looked at it yet.
Right. Right. Let me ask you this. How many problems did I assign?
You assigned 5 out of the book.
Including 420?
No,
Excluding
you
420.
didn't mention 420 last week.
So what's the problem with 420, Cindy?
Problem 420 was in the handout
The handout that
of
was
the homework 5 description.
ah, I understand now. No, let's not make the lab do this Friday. That's too much.
That's
That
great
would have
news.
been too much. I didn't really know that was happening. How did that lab thing get on the web page?
Because in 414 we have a transformation and we use that transformation to design a fan filter, and that's the lab.
Right. Um, no, forget about the handout for now. Just Friday's thing that's due is just whatever numbers I wrote on the board last Friday. That's it. We can't just pull things out of the hat last minute. I didn't realize that was got to the web page. Who put that on the web page? You and Rosita. When she asked me should I put it on the web page, I thought the numbers that I wrote on the board. I said, yeah, put those numbers on the board. But I guess I didn't realize that there was the that let's just do this. What's on that handout that's on the web? That's due the following Friday. Okay, it's not that you don't have to do it ever. You'll do it, but not immediately. Not this Friday. I think there's enough homework for this Friday. And I guess Cindy and I will discuss after class whether 420 is in or not. I guess the handout has 420 plus the lab component. Are those two related to each other? They're separate. Okay. So Cindy and I will discuss whether 420 will be on or not. So don't yet do the handout problem set until we've resolved that issue. Okay? For this Friday, just hand in the 5 problems off the book that I wrote down on the board last time. Okay? So are you guys done with that? How many people have finished that? Excellent. And how many hours roughly did it say? Less than 5.
No, I spent
More than 5. Alan? You can't remember. And around 5. Okay. And what has happened to our air conditioning? Does it do you know what is it temporary or permanent? Okay. Okay, well, the heat together with my extreme headache, that's might not make for a good lecture, but let's get started anyway. What we talked about last time, let me mark the pages here. And I would like to also briefly log in to this computer because I'm going to show some pictures of the so we want one display Dell, two display laptop, so one display Dell, Control Alt Delete. And how do I log in here? This is my own account? Oh yeah, I can log into ECS. Fantastic. Okay, it'll take a while for the login process to happen, but then we'll have um, access um, to something I put online. So what we talked about last time was um, well, my pages are all gonna fly off. Our additive and subtractive color system, right? We talked about the fact that some color systems inherently are additive. For example, when you have a TV gun system with red gun, blue gun, and green gun, and the lights um, uh, um, the right proportions of these guns get added together to produce the correct intensity or the correct color on your TV screen. Alternatively, there's the subtractive color system, and that's your what you have in your printer system, where you have cyan, yellow, and magenta, and in most systems also black. And the way the subtractive color system works is that the model for it is that you start off with white light, and each time you pass through this, each time you put like a cyan dot, then you go through a bandpass filter corresponding to cyan, and whatever that remains is the color that you end up with. And it's many times in nature we have pigments in objects that when light hits it, the object absorbs all the frequencies except for the color of that pigment, in which case it reflects it, and that's how you see things. And we talked a little bit about the human visual system and the fact that there's the model of the human eye, and there's the retina where the picture falls into in the back of your eye, and there's a portion of retina called fovea where there's highest concentrations of rods and cones, and that's really responsive for our vision, that part. So what I'm going to continue talking about today is a little bit more about um, um, let me just make it not oh, I know what it is. It's this thing. Okay, so what I'm going to continue. Oh, I see. Then you don't get any win. Okay. All right. You want to? Okay. Because if it keeps moving, all the papers keep flying. I'm not used to flying papers as I lecture. It's one more variable you have to keep track of, uh, in addition to various other things. Okay, so what I'm going to talk about today is some more stuff about modeling of the human eye. And I must preface all of these things by saying that in general, the human ear is a lot better understood than the human eye. There's linear time invariant kind of filtering that happens in the cochlea, and and uh, and we've developed things like a hearing aid that amplifies the signals and produces electrical signals that's connected to the nerve, and in general the ear is a lot better understood than the eye. There's no equivalent of cochlear, for example, for the human eye. And let me also motivate why we want to understand the human visual system. Can anybody um, can anybody make a guess or give a comment on that? I mean, other than oh, I see, you guys are from vision science. Well, other than these guys who are getting a degree in it and they really are deeply interested in it. But from an image processing system point of view, why do we care about human visual systems? Okay, well, tell me your reasons anyway. You can tell any reason. Big money? Oh, I didn't know that. Where's the where's the big money? Oh, I see. So you're thinking about therapeutic kind of reasons. Actually, there is, the LASIK thing that fixes your eye, and that's a good thing. But that's a right, right. But let's say we're not really interested in any like biological surgeries or health things or anything like that, which is kind of what your focus is. From an from an engineering image processing point of view, why is it beneficial to understand? Yeah, I'm sorry, you have to speak up because of the noise. I can't.
So just your imaging system is not over-engineered, like you don't have too high of resolution, you don't waste processing power on something like that.
Right, right, because you build a lot of imaging systems, and um, if you know something, at the end of the day, when you build the imaging system, it's the human operator or the human user who uses it. Uh, and if it's kind of like you guys studying for the final exam, right? If you know what the final exam is all about, then you can go study for it and get prepared for it. If we know the ultimate test that the resulting pictures from an imaging system will be subjected to, i.e., be observed by a human observer, knowing the characteristics of the human observer can help us design that system better. For example, if I'm designing a compression systems and I'm sending, not only do I want to save a natural resource, i.e. the bandwidth and the spectrum and all those other things, given that that's the finite resource and you want to preserve it as much as you want, and given that almost all compression systems will introduce distortions into the final image or video that you end up compressing, it would be good to put all the distortions in parts of the image that the eye won't notice. Ideally, you want the thing to be compressed in such a way that the final image looks indistinguishable from the original. And even though from a mathematical point of view you subtract two images, there's a difference between them. There's a finite amount of mean squared error between the two images, original and encoded. Uh, if the human eye doesn't see that error, it's fantastic. It didn't matter. So the reason you want to understand the human visual system is because the ultimate judge in many imaging systems is the human. Now, I said in many in many systems it's humans, but it's not in all. Can you think of examples of imaging systems that the ultimate judge or the processing that we do for images is not for the sake of humans and for the sake of, I don't know, machines? Yeah. Can't hear you, Alan. Okay, could you use the mic so everybody can? I don't know if I'm deaf today
Lithography.
because of this or everybody. Lithography. Okay, can you expand on that? For the rest of the class who might not know what lithography is all about.
So basic lithography is how they make integrated circuits. You
Mhm.
create a mask and you
Mhm.
shine light on it and then they do processing on it.
Mhm.
But then there's there's diffraction. The light system is not perfect. Whatever you design on the mask
Mhm.
does not necessarily correspond to what gets the final product of the integrated circuits. So you do what you mentioned before, where you have an image that you design image and you design the mask in such a way that you get that desired image as close as possible.
All right. In that case, you want to design a good image so that you get a functioning integrated circuit. So, so in that case, it's not for human eye to consume it. Good. Other examples? Computer vision systems, uh, where you're asking the computer vision system or machine vision system to accomplish a goal, to track a car or to count the number of cars in a highway, or to inspect an IC or to inspect the printed circuit board for inspection processes. There you're capturing images and you're trying to deduce something from them. You're trying to interpret them or find out something. Is the picture of this circuit board telling me something whether this circuit board is functional or not? Are all the solder joints properly done or not? In that case, the images are not ultimately consumed by the human observer, but more by the machine. But having said that, a good part of and then again, if you want to learn more about computer vision, you ought to probably be taking CS280. But having said that, a good part of the um, of the stuff we talk about in this course, i.e., image enhancement, image restoration, all of those things, and image compression. In almost all of those things, the human observer is at the end of the chain, and and not only for image but also for video. And in fact, modeling the human we've made over the last few years some strides as to what metric in an image to look for in order to predict what the human eye would have liked. So let's say you show images to a human observer, A versus B, and person likes A over B. Um, and let's say there's A original and then B and C are the processed. You show all of them to the human observer, and the person says, I like B better than C in terms of replicating A, in terms of faithfully representing A. And so one of the biggest questions that comes out, this is, let's say, for image compression, one of the biggest questions that comes out is what metric is the human eye computing in order for us to have these preferences of I like this image better than the other image. And people so far have come up with extremely poor metrics like mean square error. Um, and this is even worse for video because then there's a temporal aspect that's been added to the whole thing. And so in general, being able to predict what a human observer would have liked helps us design these algorithms in a better way so that we can then cater it to the final observer. So having said that, let me just start today's lecture by talking a little bit about the human visual system. So really, really roughly speaking, one can come up with the following block diagram for the human visual system. You have the peripheral level, and then you have the central level. So the peripheral level is the hardware in your eye that converts the light signal into neural signals. So if we go back to the diagram of the eye, can you zoom in please, that I showed last time. Here's the light, and the picture falls on the retina. This is the fovea with the highest concentrations of rods and cones. And this is an electrical signal. This light signal gets converted into electrical signal that gets sent into this optic nerve to the brain for higher level processing. So it's this nerve kind of signal, that neural signal that we're talking about here. So generally speaking, the central level part is not well understood at all. On the other hand, the peripheral level is slightly better understood. And there's two ways people try to understand this whole system as a whole. One of them is through physiological studies. And what that means is you just cut the eye open, and kind of like what you do in your biology classes as in high school. When you dissect a frog, you kind of dissect the eye and see, oh, what is inside. And the other one is psychophysical studies. Where you ask observers or human subjects to look at things and tell you what they've observed. And I think you guys are in the vision science program, right? Okay, you guys are in vision science, so you guys have Stan Klein in your department, right? Why are you smiling? Yeah. So guys like Stan Klein in vision science, for example, spend a lot of their time doing this these psychophysical studies. They present the observers with stimuli, and they ask them to answer questions and rate things and various other stuff. And so that's kind of the domain of vision scientists, right? Actually, nowadays there's a modality that combines the two of these things. And what modality is that? Exactly. What kind of imaging? Exactly. Functional magnetic resonance imaging, where you show things, you show objects and pictures to a human subject, um, but then they're under MRI, and you're imaging their brain as they're looking at something. And it's a combination of the two things. Is that it's psychological in the sense that you're presenting them with stimuli like Stan Klein would have done the last 40 or 50 years, but at the same time, it's trying to understand something about the physiology. Trying to see, when you look at this kind of picture, what part of the brain gets stimulated and the other part. Are you doing any work in that area yourself? Right, right. And guys, I know some people at Stanford, Brian Wendell, who does quite a bit of work on that. Actually, the functional MRI is a new thing, and it's affecting all kinds of fields. Just a week ago, I was reading in the paper that they're using functional MRI to figure out when people lie. Supposedly, when you lie, a different part of your brain gets exerted, and so they can tell that kind of as a lie detector test. Having said that, then one very simple model that one can think of in um, for the human eye is the following: light coming in, passing through some sort of a nonlinearity, and this could be some sort of a log type function, and then passing through a linear time invariant system, h of omega x omega y, so LTI or LSI system, and then out comes the neural signal. So this is just one simple model for the peripheral level. And throughout today's lecture, I'll show you the result of some experiments that support this kind of a model. Many times, if you think about the eye having a linear time invariant filter, do you think it's low pass, band pass, or high pass? Do we have evidence to know it's band pass? Right. You have difficulties in looking at very, very small spatial frequencies, and you have difficulties in looking at very high spatial frequencies. So now that I brought up this issue, I want to show figure 7.23 in Eennlb's book that shows the frequency response of h of omega x omega y as measured by a researcher by the name of Davidson. If you can zoom in, please. So when I was a student, Bill Schreiber at MIT always used to say, the eye acts as a differentiator for some frequencies, as an integrator for other frequencies. What he really meant was the eye acts as a bandpass filter. Here, in this part, it's acting as a differentiator. The frequency response of a differentiator is a straight line going up. The frequency response of an integrator is a line coming down. So, on the horizontal axis here, you have the spatial frequencies in cycles per degree, and on the vertical axis, you have the magnitude of h of omega x and omega y. And actually, in the 70s, there was a professor at Berkeley, Dave Sacrison, who published a seminal paper with his student, Manus and Sacrison, that also came up with a better characterization of that. And unfortunately, he died of bone cancer extremely unexpectedly in a matter of few years. Okay, so having said that, I'd like now to spend a little bit of time talking about some visual phenomena, specifically that explain some of the properties of the human vision. So the first thing that I want to talk about is what's called Weber's law. And this is explained both, by the way, in Lim's book and in Gonzalez and Woods. But I'm going to draw this here. So here's the experiment that you end up doing. You start with some patch that you're showing to an object, and it has, that patch has some sort of an intensity, which we call I out. Okay, and then inside this patch, you have a region that initially, let's just call it I. Sorry. Inside this region, you have a patch that initially has intensity just I, and then you gradually crank up the intensity inside this patch by delta I. So initially delta I is 0, and then you gradually increase it. And you ask the human observer to look at this thing and raise their hand when they see a just, what's called JND, just noticeable difference. Of course, you repeat that experiment many times with each subject, and you also have lots of different subjects. So not every subject is going to raise their hands all at the same time, and also not all the subjects are going to behave a similar way. But you can come up with some sort of rule of thumb and say, look, 75% of the subjects raise their hands 75% of the time, and this is kind of what we observe. And if you do this experiment, the plot that you end up getting for this thing is something like this. If I were to plot delta I over I as a function of log of I, then I get a pattern that looks like this. And this flat region is somewhere in the range of 1 to 3%. Okay? So in other words, the main phenomena that I observe is that delta I over I is approximately constant. And because there's a log here, if I let delta I go approximately to 0, then I can rewrite this as saying di over I is approximately constant, which is also d of log I. Okay.
I'm a little confused,
Yeah.
just kind of confused about
Right.
what this graph is showing. Could you
Okay,
maybe explain a
so
little bit?
what it's saying is, forget about these two ranges, okay? It's saying that for a large region of the intensity region, it takes 1% change in intensity for us, 1 to 3% change in intensity for us to notice that the circle in the middle has a different intensity than the background. Ignoring these two ends, okay? That means that if you're looking at this patch, let's say for a fixed intensity, for large range values of intensities, by just 1 to 3%, you'll notice it, and that range is fairly constant. Okay. Now there's a different kind of the fact that this, however, at the two ends, namely here and here, this doesn't hold true. That you end up being because the eye essentially doesn't have infinite dynamic range. When the intensity level is extremely small, it takes much more delta I for us to be able to notice the change, and when the intensity level is very, very high, it takes much more delta I for you to notice that. In other words, there's a saturation process going on. The eye doesn't have infinite dynamic range, right? Now we can also do, is that clear? We can also do an adaptation experiment. And so let me talk about that. And the way the adaptation experiment works is, again, you have a patch of intensity I naught, constant intensity, and you let the human observer kind of get used to the I naught. And then you have a circle in the middle, and you half of this circle you show the intensity I. In the other half you show intensity I plus delta I. Okay, so this is the left, this is the right. And you ask yourself, initially delta I is 0, so you just see a circle of constant I. And then you gradually increase delta I, and you ask yourself, under what value of delta I do you see the difference between right and left? And here, the difference between this experiment and the other experiment is that by far the majority of what the observer sees is intensity I naught. So your eye has adapted to that intensity level I naught. And if I were now to plot the result that I would get out of this thing is something like this. As a function of log of I, I can plot delta I over I. And so so if I'm looking at a particular intensity, for example, I2, then the plot is going to look like this. And this is for I naught equals I2. So your maximum, what this is telling us is that the maximum sensitivity occurs at an intensity I that coincides with the background. Okay, so the fact that the bottom here occurs at I2, and I2 is equal to I naught, means that you have that the sensitivity to intensity is highest near to the level that the observer is already adapted to. So let me write that down. So sensitivity, let me write it here. Sensitivity to intensity is highest. That means delta I over I is lowest. Near the level that the observer is adapted to. Adapted to because I naught is equal to I2. And if I just move that to I3, then the curve would look something like this. So this is I naught equals I3. And if this was the original curve that I had from the previous plot, that kind of looked like this, then these curves are going to look, I'm going to get a family of curves that are going to, for example, at I1, this would be the curve corresponding I naught equals to I1. This is I2, this is I4, I naught equals I4, this is I5, I naught equals I5. So the bottom of this curve identifies the same, it has the same trajectory as the curve that that we had before. So what this is telling you is that the sensitivity of how much change in intensity you can see is very much dependent upon the ambient intensity that your eye has already gotten used to. Okay. And that if you change, for what it's telling you is that if I'm in this part of this curve, for example, if I'm surrounded with intensity I2, it takes a lot more delta I over I for me. It takes a lot more delta I for me to see the difference between the right half and the left half of this circle than than when I'm here. So the more, so the level your eye gets adapted to is the one that you're most sensitive. Okay. Is that point clear? Okay. And the last kind of thing I want to talk about is this spatial frequency response a little bit more. So suppose we do the following experiment. We come up with an image I of x comma y, which is I naught of y times cosine omega of x times x plus some sort of a constant. Okay, and this constant is chosen in such a way that this quantity is always positive. So constant is to ensure I is always positive. Okay, and if I plot that, I get this figure 7.22 in Eennlb's book, and I'm just gonna show it to you. If you can zoom in, please. Okay, and so this is exactly what we expected it to be, right? The spatial frequency as we move from left to right increases, right? It's lower frequency here and it's higher frequency at this end. And furthermore, the intensity increases as we go from the bottom of the picture to the top of the picture. That's how we designed it. There's an I naught of y, and then there's cosine omega x of x. So that's kind of what this, if you can zoom in. So if the frequency response of the eye was completely flat, then the sensitivity that you would have across the horizontal axis would be constant. So do you see, if I cut this thing along the horizontal axis, let's say if I look at the line here, do you see things with the same sensitivity to the right and left as you see in the middle? No. Which part do you have an easier time seeing? The middle, right? The reason being, this is too low of a frequency, this is too high of a spatial frequency. Here is when we discern the black the most. So this can be used kind of as an evidence of the fact that the eye acts as a bandpass filter, or the eye has some sort of a bandpass characteristic. We're not very good at seeing extremely low spatial frequencies. We're not very good at seeing extremely high spatial frequencies. But somewhere in that mid-range, we're pretty good at seeing high frequencies. And when you go to image coding, let's say you're encoding DCT, discrete cosine transform coefficients, or discrete Fourier transform coefficients, which are almost never used for compression, but cosine is the one that's used. But that's the reason you can easily discard extremely high frequency coefficients and your eyes won't see it. First of all, for natural imagery, those have small values anyway to begin with. And second of all, the human eye is insensitive to those range of frequencies, so you can safely discard those frequencies and without worrying too much as to whether or not you've affected the human visual experience. Okay. So what I want to talk about next is the Mach effect, and this is in a picture that I want to use from this book, the Gonzalez and Woods. That's another visual effect. So let me then go to the website where I stored this thing. What happened? Do we want to start Wizard or the Classic? Anybody? Classic. Okay. Okay. So I like to go to this picture here and spend a few minutes talking about that. So what we have here is a sort of a staircase function where as you move from left to right, the intensity level increases. Okay, and what we claim is that the perceived brightness uh, looks something like that. There's undershoots and there's just before the transition from one band to the other, and there's overshoots immediately after the transition. So the perceived brightness looks something like this. So essentially what that means is that the 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 perceived brightness just before the transition here, this looks a little bit um, darker than it really is into the human eye, and right after here it looks a little bit lighter than it is to the human eye, just because it's next to the other band. So this is what's referred to as the Mach band effect. Okay, and again, it's just something that you perceive, showing you that the brightness of the images that you're looking at are not necessarily 100% correlated with what you actually perceive, and the eye can get fooled in many different ways or many different kind of directions. To show the same thing, there's also other kind of a perception type things that you can play with. What you have here is three squares where the intensity in the middle square is constant for all three of them. At the same time, uh, this one looks a lot darker than this one, simply because this is next to a very dark region, so it looks bright. This square here looks bright, whereas his one, because the surrounding region is much brighter, this looks much darker. But in fact, the actual, if you were to measure the intensity levels of these things, they'll all be the same. So again, it's the games that the human eye kind of plays with your eyes. And here's some other well-known optical illusions. There's no square here, but your eye immediately interpolates and thinks of this as having a square here. This line here is exactly the same line length as this one, but because of the way the arrows are at the two ends, this is perceived to be a lot longer than this one. In this picture, all of these diagonal lines are actually parallel with each other, exactly parallel with each other. But because of the cross lines that people have put, it looks like the lines are diverging here, and they're converging from here to here, etc. And here's the last, pardon? Yeah, right. And this is the last illusion where you've got a bunch of lines, and this gives you the illusion that there's a circle here, but in fact, there's actually none. So we talked, moving along here, we talked a little bit about the frequency band last time. So this axis is the energy of photons, this is the frequencies, this is wavelengths in meters. But just to kind of recap, there's ultraviolet at this end, infrared in between, and in this range, and somewhere in the middle there's a visible spectrum, which is blown up here, ranging from violet all the way to red, violet, blue, green, yellow, orange, etc. And then to the left, you have at much smaller wavelengths, you have X-rays, hard X-rays, gamma rays, soft X-rays, and on the right you have radio waves. I think we talked about this last time. I'm going to skip some of these things. This shows kind of an imaging system. Generally speaking, you have a scene element. There's an illumination source, like the lights or the sun or whatever the source of lighting is. And the light from that illumination source hits the object, and then it gets reflected. It goes through the imaging system, it gets reflected, and the imaging system then has some sort of an internal image plane that digitizes this and produces an output image. So this output image is digitized in two ways, right? One of them is there's finite size pixels here. Therefore, you're doing spatial quantization. The same way as if you have a time signal and you sample it, you're doing temporal sampling. Here you're doing spatial sampling. And the second way is that each of these, let's say, CCD sensors quantizes the amount of light that it's hit with to a finite number of levels. So in that case, you're quantizing the amplitude of the intensity. So there's two sets of quantization, just like with the discrete time signals. You sample a signal, you have quantization in time because of the sampling that you did, and then that gives you a digital signal. Sorry, a discrete time signal. Then you convert that discrete time signal to a digital signal by further quantizing the amplitude. And what you see here is the quantized. What you see there is the output of the quantization for both the spatial quantization and the amplitude quantization. There's one other thing I'd like to talk about this picture, and for that I would like to get the camera back down into right here. Okay. So as I mentioned, when you're doing image sensing and acquisition, there's two things. Okay. There's the illumination source. And the illumination source can be, I mean, we're dealing with image processing, so we're dealing with visible light. But in many other applications, it could be radar, which is another source of electromagnetic. It could be infrared. We took infrared lasers and we used that for CT scanning in one of my projects at Berkeley. It could be X-ray, whatever. And then there's reflection or absorption or transmitters. Okay. So this happens by the elements in the scene. All of them: reflectance, absorption, transmission. And it's this element, it's this thing that we measure in order to say something about the scene. Okay. And so when we're dealing, so this is in general. This has nothing to do with just visible light and image processing, but this has to do with all modalities of imaging. So all modalities. Now, in particular, what we have in imaging, image formation is characterized by two components. One of them is amount of source illumination. That's incident on the scene. and the other one is the amount that's reflected. Okay, so we can write this down as what we get, f of x comma y, which is the sensed signal, or the sensed image, is I of x comma y, which is the illumination, times R of x comma y, which is the reflectance. So what are typical values of I of x comma y in real life? Well, it's between infinity and 0, but that doesn't really, it's a positive quantity, but that doesn't really mean anything. Well, we can put some numbers to it. In a sunny, clear day, I can be as much as 90,000 luma per meter square, luminance per meter squared. And in a clear evening, it could be as little as, let's say, 0.1 luminance per meter square. It's a unit of light. Say that again. Right. There's a different unit that people used to use in the past called, I forgot what it's called, candle. That's right. The Lumo, I think, is the MKS. Lumen is the MKS version of that. I believe that. Right. And then the reflectance is also can take on a range of values. So that essentially tells you that the illumination could take on a very large set of values. Actually, and one of the projects that people do a lot in computer graphics and computer vision and image processing is the following: is that you've taken a picture or multiple pictures of a scene with a particular lighting condition. And now you're interested in, from those pictures, to derive another set of images under a different lighting conditions, as if you've taken it under that lighting condition. Let's say, for example, Paul Dubovik at USC. He went to, I forgot where he went, the ruins in Athens or something like that, some historic sites, archaeological sites, and he imaged the whole scene, at 10 a.m. in the morning. And given the sun's location and given the characteristics of the lighting, the illumination source, then you can play some games and some mathematical and physical kind of algorithms in order to derive the pictures you would have gotten under moonlight, for example. So that's quite an active area of research. Similarly, R of x comma y, the reflectance can be anywhere between 1 and 0. Okay, and you either reflect all of the light or none of it. It's a fraction, really. As you all know, what is the reflectance dependent upon? How much light you reflect? On the color, right? If you're wearing a dark color like black, it's on the color and the material that you're wearing. If you're wearing a black thing, then you absorb all the light, you hardly reflect anything. If you're wearing a white clothes or in snow, for example, you reflect everything and you absorb nothing. So it's of the order of 0.01. Let's say if you have black velvet, if you're wearing black velvet, 0.15 if you have stainless steel. It's 0.80 if you have a flat white wall. It's 0.9 if you have a silver plated metal. And it's 0.95 for like snow, which is white. It hardly reflects anything. It hardly absorbs anything. Okay. So so it's this function f of x comma y that in this picture, if you can switch back to the PC, it's this So if the light hits the object, it reflects some of it, and what you're collecting here is really just f of x comma y, so quantized in both the space domain and in amplitude domain. So along the same lines, if I were to cut this object with a line from A to B, then and look at the intensity that I've captured in the continuous tone image, assuming there was absolutely no quantization, this is the intensity pattern that I would get. Okay, I start off as being very bright, white area, so this is high, and there's this noise showing that even though to your eye it looks completely white, this region, in reality it goes up and down. If you have a measurement device, it has some noise. Then you hit the object, so it goes down, and as you traverse from this point to this point, the intensity gradually increases and then it decreases to this point. So it goes up and then down. And by the time you're done, this point is supposedly darker than this point, so which is why this point is lower than that point, and then comes right back up. Now here is what shows the same function there, but after it's been sampled in the space domain, right? So now you have discreteness along the x-axis here, and here is after you've quantized it also the amplitude, and so this is the quantization scale, and as you can see, it's by the time you're done with that, you get a function like this. So most images that we deal with, they've been both sampled in the space domain and quantized in the amplitude domain. And so this is a continuous image that's been projected into a sensor array, and this is the resulting image after sampling and quantization. Okay. And again, we're exaggerating here. And most times, if you sampling and the quantization is so coarse, you're going to have a lot of trouble. So the next thing I want to talk about is the notion of spatial resolution and the notion of amplitude resolution. Okay, so if you have an image, and generally speaking, you can have different spatial resolutions. You can capture an image at 1,000 by 1,000 pixels. The spatial resolution refers to the number of pixels that you've got. It can be at 1,000 by 1,000, or that same image could have been captured at 500 by 500, or 250, or 10, etc., etc. So a given image can be shown at different spatial resolutions. It can also be shown at different number of amplitude levels for the quantization, and it will all have different appearances. In the early days of the internet, when people had pictures on their web pages, and the pictures would have taken too long to get downloaded, generally what they just did is they just reduced the spatial resolution. So if you had a rose that you wanted to have on your website, it was 1024 by 1024, and at that time the high-speed internet wasn't so prevalent, everybody had dial-up, and this would have taken 5 minutes to download, then you just come up with a 128 by 128 version of it, and that's what you would have. So what I've shown here is that same image that has been subsampled successively into smaller and smaller kind of versions. And in real life, what's one of the things that you got to do before you subsample an image if you don't want to introduce aliasing? Low-pass filter. The same way as with temporal signals, time domain with one-dimensional signals, you have to low-pass filter before subsampling. That's the same thing as you have to do there. So this was an example of changing the spatial resolution. What you see here is an example of keeping the spatial resolution, but replicating the pixels. So this is the same 1024 by 1024 picture as we had here, okay, up here. But here what you've done is the effective spatial resolution of this thing is really just 512 by 512, in a sense that you've taken every 4 pixels here and you've averaged that out, and you have a pixel which covers the same amount of area on the screen as this one does, but the intensity for this superpixel is the average of 4 pixels here. And you keep doing that. This is 256, 128, 64, and 32. Now here, each one of these pixels, as you can see, this is fundamentally a 32 pixel by 32 pixel image, but I've chosen to blow it up, so the size of each pixel is much bigger than it was in this picture here. Here, as I shrunk reduced the spatial resolutions, I also shrunk the pixel size for display purposes. Here, I chose to keep the pixel sizes the same, and the end result is the same. The amount of information here is exactly equal to the amount of information in this tiny image there, but as you can see, this is not a very pleasant image to be looking at. So in general, for every pixel size and for every, if the amount of information in the image is not very high, it's not advisable for visual quality reasons to display it at a large size. Here's another interesting picture where we're again keeping the spatial resolution constant, but we're changing the dynamic range, and this is a medical image. So the dynamic range is this 256 levels here. I believe this is the original. This is the 256. Sorry, this is the original with 256 levels of amplitude quantization. So now we're quantizing the amplitude. Here's the same thing with 128 levels of gray, 64, 32, 16, 8, 4, and 2. Okay, so as you go, so let me go back. So by the time you're here, let's say moving from here to here, or even from here to here, you don't see that much perceptual change. All the way from 256 to about 64 is more or less the same. You see some bad things happening here at 64, but by now you're beginning to see some what's called contouring artifacts. And at I believe this is 16, and at 8 the contouring artifact is even more. At 4 it's this, and at 2 finally you've reduced it to a binary image, and that's quite disturbing. So the number of amplitude levels you need for most black and white images is definitely no more than 256 levels, but it can be as low as 64 or so. Meaning the eye's quantization can live with somewhere around 6 bits or so. And the last picture that I want to show is talk about what's called isopreference curves. Okay, so I'm going to deal with 3 classes of images. An image which is of a face, and this is an image with a very low level of detail. This is an image with medium level of detail, and this is an image with high level of detail. Okay, and the question that I'm going to ask myself is, there's the number of pixels n that we can change. So the same way as when we're dealing here, we changed n from 1024 to 512, 256, 128, 64, 32. And in the next experiment, we changed the amplitude levels k from 256, 128, 64, etc. Now I'm going to change n and k simultaneously, and I'm going to show it to the observers, and I'm going to ask them to tell me what their isopreference curves are. In other words, as I change n, I change k simultaneously in such a way that they say, okay, the image didn't change that much. And if I do that, this is the curve that I get. Along this axis is n. Along this axis is k, which is the number of quantization levels. So, couple of interesting observations. first of all, for the crowd image, which I'm going to go back and show it again, which has lots and lots of details in it, right? You get some sort of a almost vertical line here, which means that it almost doesn't matter that you're reducing the K level from 5 to 4. Uh, um, at this particular n value, which is somewhere around 92 or so, or 100 pixels, um, the ISO preference curve doesn't change that much. The picture looks just as good at 5 bits per pixel as almost as it does, at least to the viewers, as 4 bits per pixel. For the other two pictures, face and cameraman, face is this one, Lena. It's also called Lena, and this is the cameraman, which is in front of MIT. That's the Kresge Auditorium. For those, on the other hand, you see that the curves kind of slide down this way. Look at this region here, and what that means is that as you increase the spatial resolution, the number of pixels n, you can reduce the contrast without the observers complaining or noticing degradation in the quality of the image that they're looking at. So kind of one effect makes up for the other one. You can increase the spatial resolution, but at the same time decrease the amplitude resolution, and not people notice it so much. And that can be kind of, to some extent, that can be contributed to the fact that the perceived contrast goes up when you decrease the K. Okay, this study was done, by the way, many years ago by Tom Wong over at University of Illinois at Urbana-Champaign. And the last thing that that I want to show is the fact that even if you reduce the information content of an image to 32 pixels by 32 pixels, which is kind of what we have here. This is the 128 by 128 version of the original 1024 by 1024. You can see there's pixelation happening. This is the 64 and this is the 32. So the information content of this picture is no more than 32 numbers by 32 numbers. That's it. Even then, the best way to show it or present it is not in this way, and you can do basic bilinear interpolation or any kind of other low-pass filtering to get this picture from this picture from this picture from that, in order to give it a good appearance, even though your web page could only afford to transmit the 32 pixel by 32 pixel image. When it gets to the receiver, if you have a little applet, you can have your applet do smoothing over that. And again, that brings me to another point, which is an active area of research in image processing, is to reduce the spatial resolution and get something that has less information, but do extra processing at the other edge to enhance the edges. So this bilinear interpolation we did on this, it was a very extremely dumb, simple-minded way of doing things, and one can imagine doing a lot more sophisticated processing on this to get a better picture than that. So there is information loss as you smooth out your pixels, but you can do smart processing at the other end to undo some of the damage. I am going to almost stop now, except that I have one more thing that I want to talk about, and that is the some empirical observations. Let me just write this down instead of flashing that page, because then at the end you won't have it in the lecture notes. So if you can bring back the camera. Okay. So here's some to wrap up today's lecture. Here's some empirical observations. Of empirical observations about that are typically exploited in image processing systems. Okay. Um, Number one, and most of what I'm going to say is going to be obvious to you, but sharper images look better. We all know that, right? That's the trick people are using to get us all to buy an HDTV screen, a TV, because that's sharper. Um, if you have noise, if you're introducing noise into your system for whatever reason, either because your sensors are imperfect or because you have to do compression or whatever, it's best to introduce it in um, in textured regions rather than regions that have uniform background, because noise gets lost in the middle of all the texture. But if you have uniform background and you see noise, then it's a lot more noticeable. Noise essentially is what? High frequency. In signal processing language, noise is high frequency. So if the spectrum of the noise is far away from the spectrum of the signal, if the signal is low frequency and the noise is high frequency, it becomes very noticeable. But if the noise is high frequency, it's on the top of texture, which is also high frequency, you don't tend to notice it so much. So the same noise in uniform background region is more visible than noise in edge areas. Sorry, I don't mean edge areas, I mean textured regions. Sorry. And textured regions have a lot of edges anyway. The next property that you want to exploit is that the same noise in dark areas look more noticeable than noise in bright areas. So same noise in dark areas are more noticeable than in bright areas. And let me show you a picture of that in Eennlb's book. There's a nice example. Here we go, figure 718. And if you zoom in here as much as you possibly can, so this is a picture of some building, and we've added noise um, to both the uniformly across the entire image. Again, I'm not really sure if this comes across or not, but the noise in the bright areas is almost unnoticeable. The noise added here in the darker regions is quite noticeable. That would be the reason when you go shopping for like cars, or actually we just ended up buying a dishwasher a week ago because our dishwasher, and the guy asked, what color do you want? And I said something that doesn't show dirt and doesn't show anything. He said, that's it, you got to buy a light one, a white. Don't buy a dark color one. The dark color shows the, the, the white particles on a dark color thing, or fingerprints on a dark color ring, is a lot more noticeable than on the white one. So and this applies to your clothing as well. I can spill a lot of coffee on in this color shirt, and it doesn't show, as I'm sure you don't see it. But if I was going to wear my dark black shirt, you'll see a lot of junk on it. Okay, number 4, same amount of artificial noise is a lot worse than, looks a lot worse than natural noise. Okay, and what do I mean by artificial noise? When you do DCT, you're introducing blocking artifacts that are rectangular, and that really stands out. But if you have a camera with CCD sensors and there's shot noise from there, that's kind of a natural noise. Too many photons hit it and too few didn't hit it, etc. That looks a lot less noticeable. And then the last thing is that images with unnatural aspect ratio attract a viewer's attention. So images with unnatural aspect ratios attract viewers' attention. So that's again why when HDTV was introduced in this country, we ended up using an aspect ratio of 16:9, which is more unnatural, and there was an excuse for consumers to buy the darn system. Otherwise, people would say, "Oh, I paid the same amount of money, I get something that just looks like my current TV. It just has more pixels. Well, I'm not buying that." So they changed the aspect ratio to 16:9 from 4 to 3, and in order to kind of grab our attention and buy things. And that's also why when you go to the movie theater, what's it called? The cinemascope. It's long and narrow, and it's an unusual aspect ratio, so you tend to kind of pay more attention to it. That's all I have to say. And on Friday, we're going to embark on image enhancement. So that we'll have our first discussion on that. And homework is due on Friday too.